Esta conferencia comenzará a grabarse.
Okay, good afternoon all. So today we continue with the third webinar from this technical series, and this webinar is related to the underground, the watering and water management. So, and will be conducted by Jeremy Dowling. So for those who are not familiar with Jeremy, Jeremy is an international expert in surface and underground mine, dewatering, mining hydrogeology, water management, and water resources. And is based in Tucson, Arizona. He currently holds the position of president of Piteau Associates Group and is the chief advisor in hydrogeology. So during his career, Jeremy has led many multidisciplinary studies of underground and open pit mine dewatering, strongly focused on operational implementation, geotechnical integration, and mine design and expansion. He has a strong reputation for knowledge transfer and is the author of patents related to mine dewatering technology. He has been responsible for workflow development in areas of coupled groundwater and geomechanical prediction for underground and surface mining. His current academic engagements include advisor to the University of Arizona, Geotechnical Center of Excellence, and the School of Atmospheric Science and Hydrogeology. Originally from England, his experience encompasses over 20 countries throughout the Americas, Asia Pacific, Europe, and Africa. So that's a summary of all of the knowledge and experience from Jeremy. So if you are ready, Jeremy, I pass to you and continue with the webinar.
Yeah, sounds good. Thanks very much, everyone. Thanks, Eduardo. I'm just going to mute my camera just to make sure I've got enough bandwidth. So hi, everyone. Let's see how we get on with moving some of these slides forward. So today's talk is an overview of underground mine dewatering. Let's just try and advance the slides here. So here we go. So did the slide move on?
Yes.
Yeah, good.
Yes.
Okay, so this is just the presentation outline. So we'll just take a look at some basic drivers and objectives for underground mine dewatering, and then take a little look at the different stages of an underground mine project and what kind of dewatering measures might be needed at the different stages of mine development. We'll talk a little bit about underground block cave mining, which is kind of like the next generation type of underground mining, which has its own unique hydrogeological challenges. And we'll talk a little bit about common interactions between surface and underground mining hydrogeology. Very often underground mines and surface mines coincide, and there are lots of different groundwater interactions between them. And then we'll just quickly take a little look at different ways that you can predict dewatering requirements for underground mines. So this is just quite a basic picture that just kind of illustrates surface versus underground mine development. So in the right hand, well, sorry, in the left hand graphic, we just have a simple cross section through an ore body, and the decision about whether to develop an underground mine versus a surface mine to exploit the minerals in an ore body is usually economic. It relates to the grade of the ore and its depth below surface, and therefore the cost to strip the materials above it in an open pit mine format and then dig out and remove the ore versus sinking shafts and collecting and gathering the ore through underground mining methods. And usually the the decision is economic, and typically much deeper, higher grade minerals are mined with underground mining methods, and more disseminated lower grade ores closer to surface are usually mined with open pit methods. This cross section is quite interesting because in this particular case, this ore deposit was actually mined. It was evaluated as an open pit, but it was ultimately decided to mine it as an underground mine. And one of the reasons for doing that is that the breccia complex, which is the green material which hosts the ore, is very poorly permeable. It has very little groundwater in it. Whereas the materials higher up in the geological sequence, they're mostly water-bearing aquifer units. And through mining this ore deposit with underground methods, it was possible to basically eliminate the need to dewater those upper aquifers as part of exploiting the ore, sinking shafts down through those aquifers and then sealing them off, and then going in and exploiting the ore through underground methods. Whereas a surface mine with an open pit would have opened up all those different geological units and caused a lot more groundwater inflow as part of exploiting the ore deposit. So the hydrogeology of dewatering underground mines and surface mines is often quite different for that reason. And in fact, in recent times, as is illustrated in the bottom graphic, it's quite common to see an ore deposit that's initially exploited with surface mining methods, and then later on the deeper parts of the ore deposit that aren't economic to mine with a surface mining method are then exploited with an underground mine. So you get this combination of surface and underground mining that occur together. So why do we bother with underground mine dewatering? Probably a lot of the reasons are obvious and some of them less obvious, but again, a lot of them are economic. Mines can generally withstand a certain amount of groundwater inflow, and wet mining is common, but controlling and removing groundwater inflow to underground mines is certainly very important in order to increase mine development rates. If the mine and tunnel headings are dry, they can be driven and advance much more quickly compared to if they're wet. Also, a wet underground mine, as is the case with a surface mine, is much more expensive to operate on a day-to-day basis. And obviously, in an underground setting, if there's lots of groundwater inflow, then there's a finite amount of void space in the underground workings. There's risk of flooding and inundation, which becomes an obvious and clear health and safety hazard. So just safety alone requires that the underground mine is dewatered. So those drivers generally relate to removal of groundwater flow and volume from the underground mine. As well, if you're mining underground and the water table above is high, then you end up with high hydraulic pressures in the rock mass and in the faults and in the structures that you have to develop in order to mine. And the pressure in the rock can be a problem for the geotechnical performance of the openings and the voids and the tunnels. And so depressurizing the rock in order to improve the geotechnical performance of the mine is extremely important, and also to reduce the risk of sudden very high pressure inflows to the mining voids, which is a very significant risk in underground mining, is that you suddenly get very high pressure, large inflows. Dewatering and depressurizing the mine considerably reduces that risk and creates much safer working conditions. Something that's often overlooked as part of underground mine dewatering relates to ventilation and refrigeration of the underground mine. So most underground mines, especially the deeper classes of mines that are maybe, say, between 500 and 2,000 meters deep, they're very hot because of the geothermal gradients in the rock. And so ventilation and also cooling or refrigeration is needed. And it's needed for a number of reasons, just simply to remove heat from the mine, but also to remove gases and dust that are generated from the operation, and then to provide a supply of oxygen for the people working in the underground mine, and also for the different engines and machines that are operating. They also require a reliable supply of oxygen in order to function. And the safe maximum temperature at which you can operate an underground mine is actually considerably lower if the mine is wet and humid compared to if it's completely dry. It's a bit like walking down the street in the middle of the summer. If it's a very dry, hot day, you can withstand that heat a lot more compared to if it's a very humid day. It's the same concept. So if the mine is humid due to groundwater, it has to be cooled a lot more, in order to make it safe to work in order to make it viable to operate. And the ventilation costs in a lot of deep underground mines are very, very considerable. And the difference between ventilating a dry mine and the same mine, if it's wet, can be of the order of tens to hundreds of millions of dollars in capital and tens of millions of dollars of operating costs per year. And so there's very large economic consequences just in ventilation alone, depending on whether the mine is dewatered and dry versus a wet mine that's not been properly dewatered. This is just a quick case study. This is the Konkola underground mines in the Zambia copper belt. It's one of the wettest, if not the wettest, underground mine in the world. It's a mine that cuts through very extensive regional limestone and dolomite aquifer systems. It's over 1,000 meters deep in total, and they actually have to pump peak flows in excess of 4,000 liters a second in order to prevent the mine from flooding. So that's a massive amount of water that has to be pumped in order to keep this underground mine viable. Without a very well planned and engineered mine dewatering program, mining at Konkola simply would not be possible. And the mine dewatering program is accomplished with very high capacity underground pumping equipment and pumping stations that catches the water as it's flowed into the voids and then pumps it to surface. And also they implement a program of very deep, high capacity production pumping wells in order to help reduce groundwater levels immediately above the workings and reduce groundwater pressures ahead of the areas of the mine that are being developed. This is another example of a high inflow underground mine. This is the Nika project, which is located in central Mexico. It's in part of a district, an underground mining district in central Mexico, where you have kind of basin and range structural geology and a lot of major faults that have sheared and then had intrusive rocks placed within those major fault belts. And again, it's another karstic, or it's a karstic limestone, very deep karstic limestone setting, and very deep karstic water-filled caverns coincide with the major structures at this mine, and the water temperatures are also extreme. So there's a huge amount of groundwater inflow. There's high risk of suddenly intercepting water-filled voids and very hot water. It's a very inhospitable setting for mining, basically. And again, the entire mine operation is very highly dependent on a very well planned and executed mine dewatering program. And at NICA, they pump about 1,500 litres per second on a continuous basis in order to keep the mine dry. And in fact, this mine is actually flooded on a couple of occasions because they've suddenly mined into very large plastic caverns that are connected over distances of kilometres, and the mine voids inundate, and then they have to evacuate the mine and pump it out before they can recommence mining again. Again, it's over a kilometre deep, this mine. And so the dewatering measures, again, they include high capacity production pumping stations in the lowest levels of the mine. So basically they allow the groundwater to flow into the mining voids. It's captured and piped down to the very bottom working levels of the mine. And then there are huge pumping stations that pump the water out all the way to surface. They also have very extensive programs of underground drain drilling. So they will go into different areas of the mine and drill drains into the structures and the water bearing features and try to dewater those features, catch that water in a controlled manner and send it to the pumping stations in advance of the mining operation. So we're talking about very high rates of flow and very large pumping equipment to keep these mines dry. Just some basic factors that are often required in underground mines in order to successfully dewater them. So a lot of underground mines, the hydrogeology is very heavily controlled by permeable structures and fracture zones. And it's always important to try and target those with dewatering measures, whether it's production wells or drains. If the mine is deep, as is illustrated in the cross section on the left, then it's often important to try and avoid having to fully dewater all the different geological units and the regional groundwater system that's actually above the mine, especially if there are different layers within the geological system. Those upper aquifer units are often isolated from the underground mining workings, and so it's not necessary to try and dewater the regional groundwater system as part of being able to gain entry to the areas of ore that we want to try and extract. So very focused, localized dewatering measures that concentrate the drawdown and the dewatering in the areas of the mining operation, but at the same time minimize the amount of dewatering flow that has to be undertaken in order to accomplish the dewatering is often very key in deep underground mine settings. There's often very mixed water quality and water chemistry, which is also true of surface mining. So there may be acid generating rock materials, and when we open up the voids and the rocks come into contact with oxygen, we can get acid generating conditions and poor water quality within the actual mine voids, and it can be very important to try and segregate that and keep it separated from cleaner sources of water inflow to the mine that we may have to pump from above. So thinking about the chemistry of the water and trying to optimize the water quality of the dewatering system is another key factor. And understanding the hydrogeologic hazards too. There's some inherent risk and danger with underground mine dewatering, especially if we cross from one hydrogeologic domain to another, where the flow and the pressure conditions can be different. You can get sudden changes in the pressure regime and the flow regime that can create flooding and inundation risk. And trying to understand those risks ahead of mining and actually anticipate them and deal with them in advance of the mine plan is also usually a critical factor in underground mine dewatering. As we've already talked about, thinking about the secondary impacts of water in the underground mine, including things like the impact on the need for ventilation and the cost of ventilation, is also very important. This is just an example of a typical workflow for mine dewatering planning and implementation, and it's equally applicable for surface mining and also for underground mining. But typically, before you can plan and implement a mine dewatering system, you have to understand the hydrogeology of the location. And so screening level assessments and hydrogeologic characterization is always needed before you can develop a successful mine dewatering plan. And with that comes the development of a hydrogeologic conceptual model that considers the different hydrogeologic units and their properties and the different hydrogeologic units that are connected to the underground mine workings, but also the hydrogeologic units that may be compartmentalized and isolated from the underground workings, right? So we need to understand which hydrogeologic units and water-bearing features we need to target with the dewatering system in order to dry the mine workings out. But as we talked about before, we also want to make sure that we don't overpump and start trying to dewater aquifers or parts of the regional system that may not necessarily need to be dewatered in order to dry the underground voids out, as part of trying to optimize the environmental performance of the mine and also trying to control the costs of the dewatering program to the mining operation. So we need a good hydrogeologic conceptual model and a good hydrogeologic understanding of the site in order to be able to design the mine dewatering system. And then obviously once we've done that, we need to then go and implement the mine dewatering program. And typically, especially in the early stages of mining, as we implement the mine dewatering program and we start reducing groundwater level pressures in the rock mass and the structures surrounding the mine, we'll learn more about the hydrogeologic system. And with that additional learning that comes with the early phases of dewatering, we can then optimize the mine dewatering program for later phases of mine implementation. So the dewatering program is kind of an ongoing process all the way through the mine life that has a feedback loop where we're always doing additional hydrogeologic characterization, learning as we go, and then improving the dewatering program all the way through the mine life. So different stages of underground mine development that require dewatering, right? So it's not just the operational phases of the mine life that require hydrogeological and mine dewatering thought and attention. Typically, in the early phases of an underground mine project, some exploration tunnels or shafts will be sunk down to the ore deposit in order to start exploring it and developing it. So those early phase shafts and tunnels, they typically need some level of construction dewatering be done in order to support their construction. And then before mining operations begin, there's usually a period where a lot of underground mine dewatering, a lot of mining infrastructure is built. So the different development and extraction levels, the haulage levels, and different infrastructure needed to support mining operations is built underground. That also needs to be dewatered. And then obviously, once we actually start mining operations and we start extracting the ore from the ore deposit, then we have to make sure that that operational phase is also dewatered. And then, although it's not going to be covered much in this talk, there's usually a need to consider groundwater management after cessation of operations. During mine closure, we have to maintain hydrogeologic and environmental control of the mine post-operations and post-closure rates. So that is usually rolled in as part of the dewatering plan as well. So different types, this is just general, but there's different kind of categories of trying to control groundwater inflow to underground mines. So the most common is what you call active control or pumping, where we actually allow groundwater to flow into the mine, and we may actively lower groundwater levels ahead of mining operations with production pumping wells that could either be installed from surface, depending on the hydrogeology and the depth of the mine workings, or we could also install wells actually within the underground mine as it's progressively deepened. Water's simply allowed to cascade into the mine at the different working levels, and then it will flow down. It's collected and it will be allowed to flow down by gravity to the lowest level of the mine, where there will be big pumping stations installed, and then from there the water is pumped all the way out of the mine to surface. And in some situations, mining companies will actually develop dedicated tunnels underground that kind of circle or encapsulate the mining operations, and they will be used in combination with drain holes to kind of shield the mine workings from groundwater inflow, capture the groundwater inflow in the dewatering tunnel, and then again pump it out to surface. So those are all kind of proactive pumping-based methods of underground mine dewatering. Then there's what we kind of categorize as passive forms of mine dewatering strategy. So in these passive strategies, what we're trying to do is actually eliminate groundwater from actually flowing into the mining area and into the mining voids to begin with. So we're trying to basically plug the permeable fractures and groundwater flow paths that transmit groundwater in towards the mining voids and the shafts in the mining areas. And that is a very specialized kind of a mine dewatering approach. And it would usually involve introducing some kind of ground medium into the more permeable fracture zones within the rock mass. And in some cases, it could involve actually freezing the groundwater system, again, to eliminate groundwater flow from moving into the mining voids. And usually with passive systems, the objective is to eliminate the larger sources of flow versus completely eliminating all flow. It's not realistic to try and eliminate all flow, basically. So it's a question of trying to seal off the larger sources of flow into the mining voids. And then perhaps unsurprisingly, in a lot of situations, a combination of measures is also used. So some elimination of flow with grouting or freezing, and then some active pumping as well is often what ends up being done. This is just an example. Again, this is another project in Mexico, or at least in Central America, which is just an example of dewatering a decline that's been constructed in order to develop the deeper part of an underground mine. So the coloured, in this cross section, the coloured geological units are different ore materials that the mining company wanted to develop in an existing underground mine. So they wanted to deepen the underground mine, and the kind of red zigzag shapes are access declines down to the deeper part of the ore deposit. And the decline, as is often the case, the declines themselves are the most challenging part of the mine dewatering project. They're driven down below the water table, and so there's water inflow to the decline tunnels, but there's not a lot of space or access to implement mine dewatering or place pumping equipment into the actual decline void itself. And so a fairly common strategy, which is shown in the cross section below, you see the decline coming down, and then the green lines are extended horizontal drains, or cover holes as they're called, which are drilled out ahead of the next section of the decline, and they're drilled out from above. And the idea of those drains is that they're kind of splayed out ahead of the advancing decline in order to try and capture the majority of groundwater flow that would otherwise enter into that future section of the decline, and then also to reduce the hydraulic head present above the ever deepening portions of the decline. And so those cover holes, they're just routinely planned and drilled 200 or 300 meters out ahead of the decline, and then actually in the active advancing phase of the decline, as shown in the diagram on the right. The right is a kind of a plan view of the advancing decline. We also have these shorter. This is the face of the decline, and then these blue holes are what are called probe holes that are being drilled. They're much shorter, and they're drilled through the face of the tunnel in order to see whether there are any hydrogeologic hazards within the immediate vicinity of the advancing face, and if any hydrogeologic hazards are encountered in those holes, then again they can be dealt with and controlled before the next tunnel section actually mines or tunnels through them. This is just an example of a grouting pattern, so tunnels and declines that are going to be driven through permeable rock, in this case a permeable limestone. It's very common to undertake a program of grouting in order to make the ground much less permeable and eliminate most of the groundwater inflow to the advancing tunnel in advance of the tunnel being driven through that more permeable ground. Again, it's that process of passively eliminating groundwater flow in the major fractures that would otherwise bring water into the tunnel. And so a program of holes is drilled typically 20 or 30 meters out ahead of the advancing tunnel, and then they're all pumped full of grout under pressurized conditions, and that grout, through being pumped through all that large quantity of holes, it basically fills all of the fractures in the volume of rock in the advancing tunnel. It fills all the fractures with a low permeability medium that then renders the alignment of the tunnel much less permeable. And then as it's driven forward after the grouting program, the amount of groundwater inflow to the tunnel is greatly reduced. So that kind of program of ground treatment and ground conditioning with grouting is a very common way of implementing tunnels through permeable materials. This is just an example of an underground mine. The left-hand picture is a plan view of part of the underground mine plan, a series of tunnels and cross cuts as part of an underground, what's called a sub-level block cave. And in this particular underground mine, the mine itself is somewhat connected with the ground surface, and so during periods of heavy rain, the amount of groundwater inflow to the mine very strongly correlates with the recharge events from surface. But as well, they have a lot of groundwater inflow that occurs lateral to the underground workings, and so the mine deals with that by drilling lots of drain holes from the tunnels that surround the main part of the underground operation. And in drilling those drain holes, the actual amount of ground flow that is able to enter into the operating areas of the mine is greatly reduced. In fact, the graph on the right is a hydrograph of groundwater inflow to the mine over time, and we can see over a period of years that the groundwater inflow rate increases significantly over time. It's actually very strongly correlated to seasonal climate patterns. So surface recharge in this particular mine is a very important source of inflow to the mining operation. This is another kind of quick case study. It's actually quite unusual to see this kind of passive mine dewatering approach in an underground mine. Basically, this is an example of reducing groundwater inflow to an underground mine using a blanket grouting technique. So in this particular case, this is a hydrogeologic very simple hydrogeologic cross section. The underground mine workings are at the very bottom of the cross section, is highlighted in yellow. They're several hundred meters below ground surface. Near the ground surface, there's a shallow aquifer that feeds groundwater down through permeable structures, and that water eventually flows into the underground mine workings. And so what was actually done at this mine is they drilled some very deep boreholes down through the aquifer system into the bedrock, and then they splayed off numerous multilateral holes from the main vertical wells, and kind of created an umbrella kind of shape with multilateral boreholes that kind of form almost like a kind of umbrella kind of shape over the underground workings. And then using a program of plugs and seals, they then pressure grouted all of those multilateral holes all the way back to surface and sealed up the permeable fractures that were bringing water from the shallow aquifer down to the underground mine workings. And in doing so, they were able to eliminate most of the groundwater inflow to the underground mine workings. So that's quite a specialised mine dewatering project, and again, it's what would be classed as a passive groundwater control technique with grouting methods. So I'm just going to talk about underground block cave mining for a few minutes. This, if you like, is what would be considered the next generation of underground mining technique, and it's being used more and more commonly because it allows for much higher rates of mining compared to traditional underground mining methods. Basically, with underground block caving, the way it's undertaken is that shafts are sunk from surface down to below the bottom of the ore deposit, and then lots of tunnels are driven beneath the ore deposit to form a kind of honeycomb of tunnels underneath the ore deposit. And then once those tunnels have been put in place, there's drill holes are drilled up into the bottom of the ore deposit, and then those are blasted, almost like you do with conventional surface mining, and that causes the rock at the bottom of the ore deposit to rubberlize and break apart and mobilize. And then that material is drawn off from underneath the ore deposit, and then a zone of collapse starts to propagate up towards the ground surface. And as that zone of collapse starts to propagate up towards surface, the ore materials start to fragment and flow. And so then more ore is drawn off from underneath the ore deposit, and as more and more ore is drawn from below, so the zone of mobilized material propagates normally all the way to ground surface and causes this zone of mobilized rubberlized rock, and eventually in most cases a zone of surface subsidence at the ground surface. And this type of mining, this block cave mining, by its very nature has its own very unique hydrogeologic conditions that can change very considerably over the life of the mining project. This is just quite an interesting plot, which basically it kind of summarizes the history of underground mining through time based on the tons per day of material extracted from underground mining. And we can see that over time, the rates of underground mining in terms of tons per day have increased, as you might expect, as technology has allowed faster rates of mining. It's just purely an economic driver. As the more material you mine, the more money you make. It's as simple as that. But there's an interesting inflection that occurred in the late 1970s, and it's the rate of mining accelerated in the late 1970s, and that is mostly, if you look at most of the mines that have been implemented in this plot, at least since the late 1970s, most of them are large underground block cave mining operations, and so that underground block cave mining method has really changed the amount of ore production that you can produce from an underground mine on a daily basis. And it's really the underground block caving method is most of the future of major underground mining projects. And again, this is just an interesting picture that just shows where most of the existing or planned underground block cave mines are in the world. Not all of them, but the vast majority of underground block cave mines are implemented in existing or mature mining districts where surface mining methods have previously been implemented, but are no longer feasible to continue because the remaining ore is too deep, and the cost of continuing to expand the surface mines is too great, or because the pit slopes associated with continued surface mining are not technically viable for geotechnical reasons, or because of the land position of the mining company doesn't allow continued expansion of the open pit mining footprint. So most, but not all, underground block cave mines coincide with existing surface mining, and so the graphic at the bottom just simply illustrates the life of an underground block cave mine from early initiation all the way through to the end of its life, and it's drawing additional ore from the same ore deposit that was once exploited with a surface mine. And you can see that eventually the underground block cave mine intercepts and interacts with the old surface mine. The top left is an interesting picture of an existing mature underground block cave mine that has intercepted the surface topography. And so you can see that there's a very large subsidence zone associated with that block cave mine. And so because of that subsidence zone, there's a very large surface hydrological capture zone that is a closed basin. And so if we have, incident precipitation, a lot of recharge is held and retained within that surface subsidence zone, and that then has the opportunity to flow down through those mobilized cave materials and enter the underground workings below. And so the way that surface recharge is able to enter the cave, flow down through the cave, interact with the actual geological materials that have been mobilized within the cave zone, and then eventually enter the underground mine workings, is a very critical consideration for mine dewatering and also for safety, if the materials in the cave zone are very fine and clayey, and there's significant amounts of recharge, the water and the clay materials can combine and create some significant hazards to the underground mine workings. And you can have events which are called mud rush events, where you basically get a water and clay combination that will suddenly flow into the underground mine and cause a flooding event that is not just water, but it's a water and a solid material combined. And so understanding the interactions between the hydrogeological system, the surface water system, and the materials that have been mobilized in the cave zone are very important. And it's actually the subject of a lot of ongoing research and development within the mining industry, is understanding cave zone hydrogeology and material movement and flow as a result of that caving process combined with the hydrogeological and the surface water system. So this is just a simple kind of conceptual cross or block model through an illustrative block cave mine. And so the actual block cave mine is at the bottom of the cross section, and then the cross section just shows a geological sequence through to ground surface, and this just illustrates the hydrogeologic setting before the block cave mine is implemented. And in this particular example, there is an aquifer, which is this kind of bluey green material in the upper part of the geological sequence, and then there's a very thick aquitard, several hundred meters thick, between the aquifer and then the ore deposit, which is the kind of gold and grey materials at the bottom of the sequence. So this is about 1.5 kilometers from the ground surface to the actual underground mining area. This is about 1.5 kilometers vertical distance. So we have an aquifer at the top, the ore deposit at the bottom, and then an aquitard separating the aquifer and the ore deposit in between. And so in this particular example, as the block cave mine is operated, we get this rubberized zone that begins to mobilize and move upwards towards the ground surface. And as that happens, fracturing that wasn't previously present within the aquitard opens up. And so now we have increased vertical hydraulic communication between the underground mine workings and the aquifer at the top of the system that was previously isolated from the ore deposit. And then at a much later time during the mine life, the amount of hydraulic communication between this upper aquifer and the ore deposit increases further as the amount of fractures continues to increase. But also now we have a surface subsidence zone as well. And so all surface water that was previously able to flow away from the area is now retained within the surface subsidence zone. And so now we have the upper aquifer is able to drain through the cave zone into the underground workings. And also during the wet parts of the year, during the monsoon season, as occurs in this particular setting, we have a lot of surface water recharge, which also feeds into the subsidence zone and moves down through the cave and into the underground mine workings. So the hydrogeology of this mine, of this block cave, has drastically changed over a period of time as the mine is developed. And so understanding those hydrogeologic changes and the way that water is able to move through the geologic column, through the block cave and down into the underground workings is critically important in order to plan and implement this mine in a safe manner. This is just a quick case example from a mine in Indonesia. This is the a cross section through the Grasberg block cave mine. So the polygon here that's kind of shaded, it shows the outline of the block cave material that's been mobilized over time and is collapsed and turned into a rubble material. The ore is extracted from below at this extraction level is indicated. The block cave is surrounded by extremely permeable sedimentary sequences that include karstic limestones, and because it's Indonesia, there's very high rainfall and there are very significant recharge events on a daily basis. The steady state rates of inflow to the underground mine are about 12,000 gallons a minute, which is a lot of water. And the time it takes from a rainfall event to occur to an increase in the inflow rate in the underground mine is about a day. The vertical distance from ground surface to the underground mine is several hundred meters. So a very quick transmission of water through the block cave materials into the underground mine. But as well, there's an aquifer surrounding the mine too, which brings groundwater into the system. And so the mine, they can't do an awful lot about the climate and the recharge other than plan pumping systems to be able to control the peak inflows. But what they can do is they can control groundwater levels in the surrounding aquifer. And in this particular case, the mine's implemented a program of high capacity production pumping wells to lower groundwater levels in the geologic units surrounding the mine. And they've also implemented a very substantial program of drain drilling. So they've driven tunnels around the perimeter of the block cave, and then they've drilled numerous drill holes out into the sedimentary and limestone aquifer sequences in order to lower groundwater levels surrounding the cave in order to minimize and control the amount of lateral groundwater inflow from the regional groundwater system. So a little bit on the interaction between surface and underground mines. So as we've already seen, it's very common that underground mines and surface mines coincide together. And so understanding the relationships between the water movement and the hydrogeological conditions between the surface and the underground mine and the way they interact is often very important in order to successfully implement water control in the underground mine, but also as well in the surface mine. This is just a table that just shows some examples of some mines where there are critical interactions between a surface mine and an underground mine that is immediately neighbouring. And then this is a good example of a surface and underground mine interaction from Colorado. This is the Climax molybdenum mine, which is in the Rocky Mountains. And basically, this mine was this ore deposit was mined originally as a surface mine, and then it was converted to a block cave mine several years or a few decades later, actually. And then eventually the block cave mining was ceased, and interestingly, the mine reverted to a surface mining method. And so this cross section shows that you have an old underground block cave mine immediately adjacent to an open pit. It's not too easy to see, but this red line is the topography of the current surface mine, the open pit, which is being sunk down and is gradually intercepting all the old underground workings that are associated with the block cave. There's a very high snowfall environment, and every year a very large amount of recharge enters the old block cave materials, and it flows through a series of tunnels, some of which are intercepted by the open pit. And so on a seasonal basis, the open pit, the floor of the open pit is flooded with water that's flowing through the old underground mine and being intercepted by the open pit. And in fact, the open pit is seasonally dewatered by pumping from a shaft that is adjacent to the surface mine, that is actually connected to both the surface mine and the old underground block cave. And the photograph on the bottom right shows the bottom of the open pit during the spring snowmelt season, when lots of recharge feeds into the pit floor from the old block cave mine workings. And there's actually a plug hole and a shaft that connects the bottom of the open pit to a tunnel that connects to the shaft that dewaters all of the underground and the surface mine workings on a seasonal basis. This is another example of a block cave mine that was developed beneath an old surface pit. And again, after the surface mine was finished, the block cave operations were commenced. And in this case, a small pit lake formed in the surface mine before the block cave was initiated. And so the question arose as to whether or not the pit lake in the surface mine could suddenly empty into the underground block cave mine workings once that subsidence zone began to propagate towards the surface, creating some level of connection between the surface and the underground mines. This is another good example. This is slightly different. So this is the Bingham Canyon mine in Utah. This is one of the largest surface and underground mine complexes in the world. It's a copper mine. And all of the different colors that you see are depictions of very old underground mine workings that were developed in this district prior to any surface mining. So they were mining very high-grade skarn deposits in the early 1900s. Once that no longer was economic, all of the underground mines were closed and they were allowed to flood. And then later, in this case, a surface mine was implemented, the Bingham Canyon open pit. And as the surface mine was progressively deepened over the years, all of those old flooded underground mine workings became a significant source of recharge to the open pit slopes. And it became necessary to dewater all of those underground mine workings in order to support mining of the open pit and to allow the slopes to be implemented in a safe manner. And then in fact, the mine at Bingham Canyon, they found that pit slope depressurization was very important in order to support economic mining for the surface mine. And so they actually drove some dedicated tunnels from the lower part of the open pit in a kind of sort of conferential configuration around the lower parts of the open pit, and drilled very large quantities of drain holes towards the planned pit slopes in order to remove pore pressure from the rock and allow the slopes to be implemented in safe, dry conditions in order to improve the geotechnical performance of the slopes and to obtain the desired slope angles in the open pit design. So this was a very large scale surface mine dewatering and pit slope depressurization program that was basically undertaken using a form of underground mining technique in order to accomplish the dewatering targets for the surface mine. So just to finish up, just very quickly, prediction is a very important part of planning underground mine dewatering. You need some basis to be able to plan your dewatering measures, understand what will work, to complete trade-off analysis, compare different dewatering techniques to see which may be the most effective, to understand how much time may be involved with accomplishing dewatering targets. Normally, dewatering results aren't immediate. It takes time to pump and to depressurize before a certain target can be met. And so understanding what those time requirements are is very important. And so usually some sort of predictive tools are needed. And this slide just summarizes some of the different types of predictive tools that can be used in order to help support mine dewatering planning. So for things like simple shaft sinking and also tunnel construction, often some fairly, I use the word simple, analytical equations and spreadsheet analysis can be used to estimate tunnel inflow rates or rates of groundwater pumping needed to support the sinking of a shaft in order to keep it dry. But then also with more complicated problems where the mine is going to interact maybe with a broader hydrogeologic system or a regional groundwater flow field, very often a 3D numerical groundwater flow model will end up being implemented. So this is just an example of what we've called a four-dimensional predictive groundwater flow model to evaluate groundwater inflow over time to a set of underground mine workings. So the mine workings are depicted with all those different colours, and the different colours represent different phases of mining over different scales of time. And then the graph in the top left just shows the sinking schedule of the different shafts that were needed to gain access to the different mine areas that are depicted in colour. And so all of those things can be implemented into a numerical model that implements the mine plan geometrically in space and through time. And then that can be used, in this case, this model was used to calibrate historic behaviour of the underground mine workings. And this is just showing the model calibration. The model is shown in red, and the actual observed history of the mine is shown in blue. And what the model is doing in this particular case is it's replicating water levels in some of the shafts that were sunk into the mine workings that we were previously looking at, and it's looking to replicate the history of water levels in the mine workings over time. And in this particular case, the model was then taken and it was used to predict new phases of mining that were going to be implemented in the future, and specifically to look at how much dewatering pumping would be needed to implement additional deeping of that same mine in future years. And then this is just a quick case study of a block cave mine dewatering prediction. And so as we saw earlier, the block cave mine typically has a very transient behaviour. The properties of the rock mass involved with the block cave change considerably over time as the mine is implemented, and the moving front of mobilised rock propagates vertically and laterally. And so in order to implement a prediction of how groundwater inflow to that mine working will occur in the future requires that we have to implement material property changes to represent the block cave propagation over time. And so this is just an example of a groundwater flow model where different hydraulic conductivity zones are implemented in space and time to represent the propagation of the cave zone through the operations all the way through to when it eventually intersects the surface topography. With that, with the changes in the hydraulic properties implemented within the model, we're then able to estimate how groundwater inflow rates to the underground workings will change over time as a consequence of that block cave mine being implemented. So that was the end of the talk. Hopefully, somewhat interesting and quite quick overview of some different underground mine dewatering ideas and concepts. Just to finish up really quickly, not too sure how familiar the audience are with us, with Piteau Associates. We're a global group of technical consultants. We've got a technical headcount of about 140 different people. We've got offices in 12 locations in 8 different countries in the world, in Europe, North America and South America. And we're really, our areas of expertise are all really related to mining. Anything related to mine water management, mine dewatering, water resources and environment. We're very well known for those disciplines, and also as well mining geomechanics, in particular mine design and different types of mine facility design, and also slope engineering. We have a website, as everyone does, so if anybody's interested to find out a little bit more about what we do, feel free to check us out. And obviously Eduardo is our lead in Spain. We're very proud to have business in Spain, and we're very happy to have the opportunity to present this webinar series and talk to everyone today. So thank you very much.
Okay, do we have any questions for our presenter?
Here we have a question from Jan that said, how do you model cave zone property changes?
Yeah, so that's a very good question. So the way we do it usually is we couple the groundwater flow model to the geomechanical model. So usually a geomechanical model is built which will predict the propagation of the cave zone through time, and the geomechanical model will predict volumetric strain and change in porosity in the rock mass over time in 4 dimensions. And so you can take the volumetric strain and the porosity data from the geomechanical model and then relate that to changes in hydraulic conductivity in the different geological materials within the block cave. So with that you can develop a matrix of changing hydraulic conductivity values at different locations within the block cave over time, and implement that into a transient 3D groundwater flow model.
Thanks, Jeremy. I have one question, Jeremy, related from for the monitoring for a block cave. What kind of elements we need to use to monitoring transient changes of properties and to be sure that the watering and the pressurization program are working. Similar than the ones we use in the open pit, so vibrating water sensors installed in depth, etc. Or there is other things that we can focus on.
Yeah, it's not. So it's actually a very challenging problem, because the block cave zone is mobile, and so actually putting instrumentation within it is inherently very difficult, and most of the sort of mainstream instruments will quickly break. They'll share and basically break. And so it's actually, you know, block cave monitoring is the subject of quite a lot of ongoing industry research and development. But typically, the only real way to calibrate the material property changes is through observing the inflow regime in the underground workings themselves, and then back calibrating those inflow rates over time to a groundwater flow model that has some reasonable property ranges assigned to it, and then, you know, adjusting those properties until they show a match with the observed inflows.
Mm-hmm.
But actually getting inside the cave zone and seeing, you know, what the real, you know, physical properties of the materials are is inherently very difficult. You're really limited to actually looking at the sizes of the fragments that come out of the draw points in the mining operation.
Mm-hmm.
I've got one question, Jeremy, which is related to the barn roof plugs. Do you use that quite often, or it is better to case the hole? So up to what amount of the weathering may use the plugs, or when do you use the properties of the casing capable of retaining the water influx? What do you think is better?
Sorry,
Thank you.
Could you say that one again?
It's related to the roof, barn roof plug that you use on the mother hole and some holes which are the daughter holes as well. So you use it for cementing and wedging, right? So it prevents the water to get into the hole. I mean, to what certain amount of flow rate you may use the plugs, or when do you consider to use the casing of the hole as being more effective, the casing than the plugs? Do you have any case in which you had to case the hole?
Yeah, so those all of those daughter holes or multilaterals were basically open holes, and they were pressure grouted. So they were pumped full of grout under, you know, X amount of pressure in order to fill the fractures in the formation with grout and render them impermeable. So the plug prevented the grout from flooding back into the materials above.
Yeah. Okay. Thank you. Anybody else got more questions?
I have one. Jeremy, always we focus more in the watering and the pressurization that are the key issues with an underground mine. But I think it's also relevant to use the watering program to try to avoid generation of contact water inside the underground mine, and also try to achieve the watering or the discharge permit. So is there any kind of recommendations when a mine excavating the underground levels to try to avoid that?
Yeah, so sorry, the sound quality is not very good, but most underground mine dewatering operations will consider the chemistry of the water in the different domains that need to be pumped in order to achieve the mine dewatering targets. And if there are clean hydrogeologic or fresh water, good quality water units within the hydrogeologic system that can be dewatered and segregated from the dirty water that's flowing into the actual mine voids themselves, then typically the mine company will try and segregate the different types of water in order to minimize their burden of water treatment. So once the water's come into contact with the underground voids, usually it's considered contact water. But if you can pump it from higher up the geological sequence and retain it as a non-contact source of water, then it can be potentially handled differently, right? So segregating the different waters versus having them mixed is usually a pretty important consideration for the dewatering program.
Good, thanks. There is anyone with other questions? It seems no questions. So Carlos, if you want to close.
Yes, thank you much. I would like to just thank Jeremy and Alfredo for what you've done today with us. It's a pleasure to have you in our institution, sharing all your knowledge, for your kindness and holding these webinars, and we're sure that it will increase our knowledge about the water management and mining operations. Your experiences will always be welcome in our institution, and we thank you very much for all what you've done and participation in our educational project. Thank you, Jeremy, and thank you, Alfredo.
Yeah, thanks very much. We really appreciate the opportunity to give these presentations. It's our honour to be here. Thank you very much.
You're welcome, Jeremy. You'll always be